4.4. So we're going to talk about page 5 of the handout a little bit, even though there are no problems there, before we move on to the new topic. Let's still got a couple. Five, 4, 3, 2, 1. Roll them. All right, we're. Okay, so homework due, right? And so this chapter 4 is really a lot of theory, right? We keep plunging deeper and deeper into some of this theory, and I think the light's going to start coming on in 4.5 and 4.6, like things will get simpler. But just, I want to say a little bit more about page 5 of the 4.4 handout and talk about this word isomorphism. On the handout, we just say a linear transformation that is both one-to-one and onto is called an isomorphism. So if both those properties are satisfied, well, three things in a way. It's got to be a linear transformation, it's got to be one-to-one, and it's got to be onto. Isomorphism is what we call, is the word we use for equivalence of vector spaces. So when two vector spaces are isomorphic, if there's an isomorphism between them, they are essentially the same. They're equivalent in some way. They might not look the same, but the isomorphism gives a one-to-one correspondence that matches them up. And in particular, this theorem 8 just says an abstract vector space that has a basis with n elements is isomorphic to Rn. So we're saying if you have, in that picture, if you have a vector space V, and I guess what I should have added to my picture is it's got a, oh, I can't write anything today. It's got a basis with n elements. So that's crucial for this picture to work. And then you associate to a vector x this thing, the x, b, which are the b coordinates of x, which is a column vector in Rn. These two guys are essentially equal or the same. And so what does that mean? The example I put on the handout is as a vector space, P5, now I just chose a value at random here, okay? I could have picked any Pn, is isomorphic to R6, actually. Now, P5, what are the elements of P5? They're polynomials of degree 5 or less. Why did I pick 5? So it's P of t like a t to the 5th plus b t to the 4th plus c t cubed plus d t squared plus e t plus f, all right, just a polynomial of degree 5 or less. What this isomorphism is saying is that if we just work with a column vector of those coefficients, so just a, b, c, d, e, f, which is a column vector in R6. So there happen to be 6 because we also have the constant term as a coefficient. Anything you want to show about the polynomials in this vector space P5, you could just as well show it using 6 component vectors in R6 because of this isomorphism. So some of those polynomial exercises you could work through by working in the corresponding Rn space, which is always going to be one-dimensional higher than the number you see on the subscript here for P. Or you could work with the polynomials. So I'm not going to say any more than that. The book kind of hints at it. But if you prefer to work with the polynomials, all those exercises work just as well as far as linear independence and basis and such, okay? So really, when I see this guy as an element in a vector space, a polynomials, kind of in the back of my mind, I just see these coefficients as a column vector, because anything I do with these column vectors matches up exactly with anything we do with polynomials. And that's all we're going to say. We're going to move on to 4.5 now and get started on a new section. So 4.5 is all about dimension of a vector space. And so a few theorems to get warmed up. Theorem 9, I don't think I need to project these. Theorem 9, if you don't have one, let me know. You should have a 4.5. If a vector space has a basis of n vectors, then any set of vectors containing more than n elements must be linearly dependent. Once you have a basis and you know how many elements are in there, so n, any set with more than n elements must be a dependent set. So in a sense, a basis is a largest possible linearly independent set. And I'm not going to go through the details of the proof. That's just for you. Theorem 10, if a vector space V has a basis of n vectors, then every basis has n vectors. And you probably already kind of assumed that had to be true. It's not obvious that it has to be true. If you have a basis of n vectors, to me, in my mind, it's conceivable that there might be a different linearly independent set that has more than n vectors, but that's actually impossible. And it really just takes a little bit of logical reasoning to see that. So once you find a basis for a vector space, and you see how many vectors are in that basis, every other possible basis has to have the exact same number of vectors. And then turn the page to page 2. So if a vector space V has n vectors, where n is some positive integer, we say V is a finite dimensional vector space, and the dimension of V is n. So the dimension of a vector space is just equal to the number of vectors in a basis. If you find a second basis, it's got to have exactly the same number of vectors. So we write DIMV equals n if the dimension of the vector space is n. So DIM stands for dimension. Some examples. The most boring example is the zero vector space that has just one vector, the zero vector in it. We say it has dimension 0 for convenience. Don't worry about that. If a vector space has an infinite basis, then we say the vector space is infinite dimensional. Most of the vector spaces we look at in a class like this are finite dimensional. But the one example of a vector space that's infinite dimensional that we've looked at is the continuous functions on an interval, that C of 0, 1. There's no finite basis for that kind of vector space. Rn has a basis of n vectors. for each positive integer n. So the dimension of Rn is n. So the dimension of R1 is 1, dimension of R2 is 2, dimension of R3 is 3. So dimension here matches up exactly with geometrical dimension, just what we would expect. And for that polynomial space, so P sub n, here I'm representing all those different possibilities at once, right, with n. P sub n has a basis of n plus 1 vectors, so the dimension of P sub n is n plus 1. And here again, this example from the previous handout, the dimension of, we would write dim of P5 is actually 6, not 5, because we need that one extra constant for our constant term of our polynomial, right? So if you just think of how many terms are involved, it's not hard to see. That's dimension 6. All right, let's do an exercise now. And this is a good little one for us to do together. So find a basis and state the dimension of the following vector subspace of R3. So we're looking at this guy, 2a plus b plus 3c, a plus 2b plus 3c, 3b plus 3c. So we're looking at 3-component column vectors. So those are vectors in R3 such that a, b, c are in R, are any real numbers. So we want to find a basis for this subspace. And we're going to state the dimension. Of course, once we find a basis, the dimension is easy. The dimension is just how many vectors are in the basis. And here, it's given that this set is a subspace. So in an earlier section, I might have asked you to verify that such a set is a subspace. And we've seen examples where we have this kind of description. Sometimes it is a subspace. Sometimes it's not, right? But here I'm not, you don't have to verify. We're going to do something else. So we've already verified that the vectors of this type form a subspace. We're going to try to find a basis. And I think we know what to do here. We want to try to find a spanning set for this subspace. And we've talked about how we can write this as A times a certain column vector plus B times a certain column vector plus we got a C times a certain column vector, right? We can express the elements of this set in the following way. And the coefficients of A are, 2, 1, 0. Coefficients of B are 1, 2, 3. Coefficients of C are 3, 3, 3, right? So we can say this subspace is actually equal to the span of 2, 1, 0, 1, 2, 3, and 3, 3, 3. And actually, by that, we've just verified that it must be a subspace, because any span, the span of any set of vectors is a subspace, right? Is the set of 2, 1, 0, 1, 2, 3, and 3, 3, 3 a basis for this subspace? Basis for this subspace. I mean, it could be. I heard a no. I only heard one no, though. So we haven't finished our voting yet. We need our clickers, like in physics class. Everybody vote now. What would have to be true for it to be a basis? There are two things that have to be true for a basis. Yeah, they have to be linearly independent vectors, and they have to span the subspace. So we know they span the subspace because the subspace is their span, right? So that property is satisfied, the spanning property. But the question is, are they linearly independent? If they are, they're a basis. If they're not, they're not. There are a lot of ways we could answer that question. How would you answer that question?
Well, you can add the first two vectors together.
Yeah. So clever answer. We have some clever people in the room. We have lots of clever people in this room. Just observe that 2, 1, 0 plus 1, 2, 3 equals 3, 3, 3. Right? If you add the first two, you get the third one. Now, if you just happen to observe that, so the three vectors are not linearly independent, just from that fact, right? Because one is a linear combination of the other two. So that's one way. And again, you're done if you see that. But that's not always so easy to see. Or what if, the third one could be a linear combination of the first two in a non-obvious way, too, right? So the second way, kind of the kind of following the straight and narrow path, another answer could be to check to see if the matrix 2, 1, 0, 1, 2, 3, 3, 3, 3 is invertible. And it's not. And how would you check to see if it's invertible? Yeah, you could do the determinant. Everybody likes to determine it. I mean, you could just row reduce also. You could check to see if you have three pivot positions, right, then the three columns are linearly independent. You could check to see what the column space is. If you call this A, you could check to see, does AX equals 0 have non-trivial solutions? Right? So that's kind of a thing we've done a lot. But again, you could just check the determinant. We have all those equivalencies because it's a square matrix. So there are all those equivalencies to invertibility. Or does AX equal 0 have non-trivial solutions? This would actually work even if we had a non-square matrix situation. So maybe we want to highlight that method. That's maybe the most general thing to check here. And again, the answer is, I'm not going to go through those steps. Ax equals 0 does have non-trivial solutions. So again, the three vectors are linearly dependent, and they do not form a basis. Now, what you can do then is, since we've already observed that the third is the sum of the first two, is 2, 1, 0, 1, 2, 3 a basis? Well, we have to verify two things. So verify that the span of these two equals the span of the 3, 2, 1, 0, 1, 2, 3, and 3, 3, 3. So that if we remove that 3, 3, 3 vector, the span is the same. And I mean, this statement, again, is a shortcut way to show that, because you can get the third vector from adding the first two. Again, if you didn't see that obvious relationship, the long way is to solve 2, 1, 0, 1, 2, 3 times x1, x2 equals 3, 3, 3. The short way, again, is to just make this observation if you're lucky enough that you can add those two together, right? So if you solve this system, you're going to get, I think, 1, 1 as a solution, all right? So that's true, that the span of those two is, and then we also have to verify that the two vectors 2, 1, 0 and 1, 2, 3 are independent and that should be real easy for you guys. There's sort of a long way and a short way here too. What's the short way? Everybody knows, right? Yeah, when we like two vectors, because just like Robin's saying, the only way they could be dependent if one is a scalar multiple of the other. And there's no way to multiply 2, 1, 0 by a scalar to get 1, 2, 3. You know, the 0 is always going to stay 0 no matter what scalar you use, so you can't get 1, 2, 3. And if you don't use that two-vector trick, you would have to go back to this kind of check in this case, where, of course, the A matrix is the matrix with these two columns, right? So if you took this matrix times x1, x2 and solve for 0, 0, 0, you'd have to show that there's only one trivial solution, a unique solution. Yeah?
So when you say we have to verify that those two vectors is equal to the span of all three, why? Because isn't that already a theorem? That we can omit the spanning set theorem? That we can omit a linear dependent vector?
It's not clear which one we can omit if we don't see this relationship. So, for instance, if these two, say these two, now I'm getting kind of abstract, were scalar multiples of each other, and this one was independent of those two,
Yeah.
if we throw this one out,
Yeah, that would.
then we've lost our original space. So there's no rule that says if you remove the third one, you'll span the same space if they're dependent. The spanning theorem says if these three are dependent, you can remove one of them and you'll still have the same span. Now here it's kind of, we all know which one. But in general, you won't necessarily know it's the third one that you can remove, right? Here I think it doesn't matter which one we remove, because because we only end up with two vectors, we're always going to end up with two vectors that are not scalar multiples of each other. Is that? Yeah. And so again, I'm not writing out the statements of the verification we're talking about, but you would actually have to say something here. Like you would have to say, since these are not scalar multiples of each other, since the columns times x equals 0 has only the trivial solution, they are independent. All right, and then, so we're finally ready to answer some questions. So just to finish things up, so therefore that set of two vectors 2, 1, 0, 1, 2, 3 is a basis of the subspace, and the dimension of the subspace is 2. So the dimension of the span of these three vectors is 2, two-dimensional subspace. That's a good test problem. Ready to move on? All right, so next page is Theorem 11 on the handout. Has two parts to it. And Theorem 11, I think, will embrace almost very intuitively. Part 1 says if H is a subspace of a finite dimensional vector space, then the dimension of the subspace is less than or equal to the dimension of the space. And that's a real powerful theorem in linear algebra. And the typical example to give is consider subspaces of an R, like R3. The subspaces of R3 can only have dimension, well, they can have dimension 0, 1, 2, or 3. So when you're in R3, a subspace of R3, the zero-dimension subspace is just the origin all by itself, 1 point, boring example. Any one-dimensional subspace will be a line through the origin, geometrically. It's got to include the origin, because to be a subspace, it has to include 0. And so all lines through the origin of R3 are one-dimensional subspaces. A two-dimensional subspace is a plane that includes the origin. And all planes through the origin are two-dimensional subspaces. And then what's kind of interesting is, can you have a three-dimensional subspace of R3? It turns out R3 is the only three-dimensional subspace of R3. So if a subspace has a dimension equal to the space, it's got to be the whole space. You can't have a three-dimensional subspace sitting inside of R3. Theorem 11, part 2, let H be any finite dimensional vector space. Any linearly independent set of vectors in H is already a basis or can be expanded into a basis. So there's kind of two directions we can go on when we start out with a set of vectors. If they're independent, they can always be the beginnings of a basis. We can add vectors to them till we get a basis. If we start out with a spanning set, like we were in this previous problem, we can always reduce that set down to a basis. So there's this idea of expanding an independent set to get a basis. There's also this idea of reducing a spanning set to get a basis. And Theorem 12 on the next page, page 4. So the basis theorem is let V be a vector space of dimension P. P is greater than or equal to 1. Any linearly independent subset of V containing P elements must be a basis. And any subset of V of P elements that spans V must be a basis. So let's just paraphrase these, because these are two important ideas. So if we have a space of V where the dimension of V is equal to P, any independent set of P vectors is a basis. And in the, I don't know, my crazy graphic on the handout there is really part A. If you have P elements that are linearly independent, that automatically is a basis. So any independent set of P vectors is a basis. And the other part of that theorem is if you have P vectors that span V, then they are a basis. And why the logic here is, if you have an independent set of P vectors, they're independent. What's not totally obvious is that any independent set of P vectors will have a span that's equal to the vector space. So in the theorem, the proof of the theorem, you'd have to verify that this set of vectors has to span the entire vector space, and then that implies that it's a basis. For the part B portion of the theorem, if you have P vectors that span V, okay, their span is the vector space. What's not obvious is that they must be linearly independent. But it turns out they must be linearly independent. That's kind of interesting. Any set of P vectors that spans the space can be shown to be linearly independent, so it's automatically a basis. And that's the point of the spanning theorem. I'm sorry, the not spanning theorem, the basis theorem, theorem 12. And next page, let A be m by n. We can get back to the null space and the column space of A. So here A is an m by n matrix, not necessarily square. We can talk about the dimension of the null space of A and the dimension of the column space of A. And now we've already worked through describing the null space of A. I think we've already found a basis for the null space of A. We know how to find a basis for the null space. How do we find a basis? We take the matrix and we solve AX equals 0. We describe the general solution. We're going to actually be given free variable times vector plus free variable times vector, right? We're going to be taking a linear combination of a certain number of vectors where the weights are the free variables. Those vectors are linearly independent. They form a basis for the null space. Well, those vectors that we get when we solve the AX equals 0, the homogeneous equation, there's one vector for each free variable. So the dimension of the null space is always equal to the number of free variables. Right, we're going to have one basis vector for each one of those free variables. And the dimension of the column space, well, we get basis vectors for the column space from each pivot column. So that's just the number of pivot columns. So that just sort of falls out of using what we already know about basis and now applying it to this concept of dimension of a space. And let's do an exercise. So here we want to find the dimension of the null space, dimension of the column space of A, where A is 1, 0, 0, 0, 5, 1, 0, 0, 3, 0, 0, 0, 6, 4, 2, 0. We want to find the dimension of null A, dimension of column A. You can just read them off because I gave you an example here. This is already in echelon form. It's not reduced. So we have the zeros below. We don't have the zeros above in the pivot columns, right? But the idea is once we get to echelon form with the zeros below, we know where our pivot positions are. So to figure out what's going on here, I need to look for pivot positions. I have one here, one here. There's no pivot position in the third column and fourth column, right? What's the dimension of the null space? 1? Because we would have one free variable if we think of solving AX equals 0. X is going to be a 4-component vector. And each column here corresponds to one of those variables, right? So actually, x3 is a free variable. So if we actually solve the system and describe the general solution, I know already I'm going to end up with just x3 times some constant vector, right, in my general solution. So the dimension of null space is 1. Dimension of the column space, we just learned this last time. We just look at the pivot columns. 1, 2, 3. Dimension of column space is 3. Because we know those pivot columns span the column space, and we know those pivot columns are linearly independent. So that's really just a short answer once we have the results of our previous theorem. Do we want to? So what I haven't done is I haven't given you a basis for the null space, right? Basis for the column space, we can see. We can just take the actual pivot columns, right? So make sure I would say you already know how to find a basis for the null space of A, right? And what you would do is you actually got to finish the process of row reducing A, and you can actually work right from this form. Do you want me to? I wasn't going to do that, but you want to do it? You want to see it? Oh, I had one head nodding. So again, we would finish the process of solving the homogeneous equation. I think, I can get the solution even from this point before I've totally reduced, because I would have x1 plus 5, x2 plus 3, x3 plus 6, x4 equals 0. I have x2 plus 4, x4 equals 0. I have just 2x4 equals 0, right? So I'm just going ahead and writing out the ax equals 0 components as it stands right now. Well, this implies x4 is 0. But if x4 is 0, then we can work backwards. I'm basically doing the reduced form in my head from the equations here, right? If x4 is 0, then x2 must be 0. And so if x4 is 0 and x2 is 0, so this is gone, we know x3 is free, so all we're left with from the first equation is that x1 is negative 3x3. So if you don't like what I'm doing here, just reduce this matrix all the way, right? And then the results will pop out. I'm just working from the algebraic equations instead of the matrix. So we end up with x1 equals negative 3x3. x2 is 0. x3 is free. x4 is 0. And so our general solution to ax equals 0 would be x equals x3 times negative 3, 0, 1, 0. And there's our one-dimensional basis, right? So I would say that one vector, negative 3, 0, 1, 0, all by itself, is a basis for the null space of A. So again, doing a little bit of a shortcut to get to the solution. The idea is, as soon as we identify how many free variables there are, we know the dimension of the null space. I don't have a basis. I can't see the basis of the null space just by staring at this matrix at this point, though. I would have to get all the way to the description of the general solution before I could actually identify basis vectors for the null space. Column space is different. Column space, the pivot columns give me the dimension, number of pivot columns gives me the dimension of the column space, and I can actually use those pivot columns as a basis for the column space. In fact, I have to use the original matrix's columns for the column space basis. I cannot use any columns I get to along the way for the column space basis. Okay. And I got a little blurb there down at the bottom, which is a thought worth stating. I realized I've been a little bit loose with language on some of these statements. We're only talking about finite dimensional vector spaces when we talk about these rules about the number of vectors in a basis. So for a finite dimensional vector space, any linearly independent subset of V can be expanded to a basis if it isn't already a basis, and any subset of V that spans V must contain a basis for V, and then fine print there as long as V is not the zero vector space, which it won't be for us. Okay. All right, so we still got 5 minutes, so we can go a little bit further today. I just prefer to do this because there will be that day where we'll be a little short on time. This saves us. Oops, I forgot to punch. Sorry about that. So these are not pre-punched. So we're ready to move on to something called rank, which some people think of as the most profound idea about matrices that we talk about in this course. So it's a big deal, the rank of a matrix. And I know I got just a couple more minutes before we got to finish, but let's take this off. So this next section starts out with the idea of row space of a matrix. And the row space is a subspace spanned by the rows of A considered as elements of Rn. So my example that I give you guys there is 2, 1, 6, negative 1, 5, 0. Now, for us, vectors have always been column vectors in Rn. But here, we're going to think of 2, 1, 6. We're going to call it a row vector. And I think our book still likes to use just old-fashioned parentheses and commas for that. We have another row vector, negative 1, 5, 0. We could write them this way. There's no law against doing that. But it just gets very confusing because we don't want to confuse them with columns of a matrix. So we are just thinking of them as vectors with 3 components. So they're elements of a 3-dimensional vector space. But we're always going to write them sideways because the columns are something else, and we just don't want to confuse those in our notation. So now we got this thing called the row space of A. Is just the set of all linear combinations, right? A times 2, 1, 6 plus B times negative 1, 5, 0, where A and B are in R. So it's totally analogous to column space. And I guess it's all on our handout. Theorem 13, part 1, if 2 matrices are row equivalent, then their row spaces are the same. And I think I'm just going to stop today with that thought. So row equivalent matrices have the same row spaces. That's not really true for column spaces. And we'll investigate this more next week. So, see you.